So, hello, let's solve Mext exam, physics exam 2009 undergraduate. So, he told you that we have a plane mirror is placed horizontally at the bottom of a transparent liquid of 10 centimeters depth. When one looks at the image of a small object floating off the surface of the liquid, right above the object, the image is seen at 40 centimeters below the surface of the liquid. Find the approximate value of the index of refraction of the liquid. So, what is this problem? Well, this is a combination of plane mirrors, okay? Plane mirrors with this type of problem. Now, if you studied optical geometry, you've seen this. This type of problem, I took these pictures from Google just by searching like problem of the fisherman. You can find this easy. So the moment the moment we the moment you are seeing the fish, you see it a bit above where you should be seeing it. Like here, the light beam is going out. He goes out here, but the moment he is going out to the air, he tends to go there instead of going like this. Why does it go like this? Because the light begins to be faster, right? Snell's law. We are going to see everything now because I'm going to deduce everything with you. So let's just, I don't think we're going to use this photo anymore, so put it out there. So just so that we can explain the question better, you are standing here, okay, and there is a mirror over here, okay. There is a mirror in the bottom of the water. Mirror, this is 10 meter or centimeters, 10 centimeters, 10 centimeters, okay. So when you look over here, you end up seeing your reflection like this. You see yourself over here, okay. So you see a reflection over here, and this is 4. Why is this 4? Because he told you that this is 14, okay. Over here he told us, you see the image at the from the surface is seen at 14 centimeters below the surface of the liquid. So it is 14 centimeters before the below, okay. So over here. So now a question: without water, where would you see your image? If there was no water, this is a mirror. Well, would you see it? Well, you would see it 20 centimeters down, because if you are here and there is this mirror over here, this is 10 centimeters. You see yourself. This will be 10 centimeters, and here will be your reflection, right? So notice that the real image, the real image, complicated. The image without the water is somewhere over here. Is somewhere over here. Okay, being this 20 centimeters. Okay, 10 from here to the mirror and 10 downwards. Okay, is this clear? So now we are going to find the formula to see why, because notice what's happening with you over here. It's happening the same as for the fisherman. You should be seeing your reflection downwards, this one over here, but you're not seeing this one. You see this one over here. Why? Because the water is messing the view. Okay, so how this happens now, for the next laws, you need to remember the Snell's law. If wow, that was a straight line. So if light comes over here from, let's say, medium n1, and here this angle over here that it makes with the normal, okay, and here we have the bending light, and here n2. Now a question for you is n is the velocity, where is the velocity bigger, in n1 or n2? In n2. Why? Because of this law over here. In n1 it's bigger, okay, in n1. Sine of theta 1 is equal to n2 sine of theta 2. Snell's law. Snell's law. Okay? Now, another thing, now many of these things you don't really need them. If you know this formula, you just solve this question, okay? But let's use this to discuss, because there are other questions that use Snell's law in the Mext exam, so it's useful. So n is index of refraction, okay? And it is defined as being the velocity, and now I always forget which one is dividing, so how can you know? It's easy. It is c divided by the velocity in that, the velocity of maybe the light in that medium over there, okay? So this is the velocity of the light in vacuum, c, and this is the velocity of the light in that medium, okay? So supposing here is not the vacuum, if this was the vacuum, it would be c divided by c, which will be 1, because it might be a bit of difference, so it's 1, it's considered 1. For the Mext question, whenever it's talking about the vacuum, it will be 1, okay? So c divided by v1. I remember this division because n usually is bigger than 1. It's always bigger than 1. So this is the, so you need to have c above, okay? So notice something over here. Let's use this over here, okay? Just so that we can understand it. So here c divided by v1 sine of theta 1 must be equal to c divided by v2, because n2 is equal to, by definition, the velocity of light in vacuum divided by the velocity of light in that medium over here. It might be glass, water, anything, okay? So sine of theta 2, okay? So using Snell's law. Now what's happening over here? You can cut c, so you'll have that v2 sine of theta 1. Now notice how sine of theta 1. Notice how this changed. This was n1 theta 1, but here v2, okay? And here we'll have v1 sine of theta 2. So now let's talk about this that we just found, okay? If v2 is bigger than v1, okay, v2 is bigger than v1, so this angle over here must be smaller than this one. Why? Because here it's multiplying, so v2, a number that's bigger than v1, okay, is multiplying something, and v1 that's smaller than v2 is multiplying something, but they are equal. So if v2 is bigger than v1, so sine of theta 2 must be bigger than sine of theta 1. Why? Because this is the smaller number, let's say, for example, and this is sine of theta 2 multiplied by it. But if this is smaller than this, so it needs to be multiplied by something that's bigger than this one, so that they can be equal. Does this make any sense? Okay? And this is why it feels like it's running away from the normal, Why is it running away from the normal? Because look, the velocity of the of the light in the air is bigger than it is in the water. So this angle over here gets bigger, okay? Because this sine of theta when it's going out must be bigger. So whenever the velocity in the medium that's bigger gets the sine bigger, okay? So this is important for a question from physics, I think in 2015, something like this, uses these notions over here. And this is like this law over here, even like there is an article like about dogs, how they go like many things in nature do this, like it's like they choose to optimize their path, okay? So this is the first thing that you need to know. The Snell's law that we've been talking about and discussing over here, this relation between the velocity and the angle, important, okay? Now we are going to use this picture over here, okay? So look, this is the normal over here, okay? Let's say we have an object over here, okay? So this object over here is going to emit light, okay? So the light is going out of it, and this is the medium n1 from where the light is going out, okay? And and here the medium n2 is from where the light is going to, okay? So now let's say that it should, if it was the same medium, it would have gone like this, but as it will go like this, okay? Now you already can see that the velocity in the second medium is bigger, right? Because its angle is bigger. You can think about it like the light when it's faster, it's tend to run faster from the normal over here. This is the normal, okay? So here we'll have an angle theta 2, and here we'll have an angle theta 1, okay? And this is, so for someone that's standing over here, what he's going to see is that the light, because we think that the light goes only straight, so we think that the object is over here. So we'll say that it is a small d just, okay? Where actually it was over here, where is big D over here, okay? So over here, okay? And here, let's call it X, okay? This distance over here. Now, this angle over here, this line over here and this line are parallel. So this angle over here is theta 1, okay? Okay. And this angle over between this line and this line over here is what? This angle over here. This is theta 2. Why? Because look, it is like this. This is theta 2. This needs to be theta 2 also. Can you see it? Like this is the line and this. Okay? So this is theta 2. Now notice, if you can you see this z over here? This z over here. Okay, so this angle over here is equal to this angle over here. Now my drawing is awful, but by the rules of mathematics, this is the same, okay? We have parallel lines. This is theta 2, so what, we have parallel lines, and like this, right? So this is theta 2, so this must be theta 2 also. So this angle over here is theta 2 also, okay? Now notice, I'm going to draw this triangle over here, okay? So this triangle over here is dx, and here is theta 2, okay? And now I'm going to draw this big triangle over here. okay, which is like this. This is x, here is 90 degrees, right? 90 degrees. This is big D, and this is theta 1. Okay, just taking these two triangles. Now we are going to use that the tangent of theta 1 is equal to the opposite divided by the one by its side, right? So the opposite x divided by d. And the tangent of theta 2 is equal to what? To the opposite divided by its side. Okay? So now we will have that the tangent of theta 2 divided by the tangent of theta 1 is equal to, so x divided by d multiplied by d divided by x, right? Because we are dividing, so you can flip it and by multiplication. So x divided by x. So we have that the tangent of theta 2 divided by the tangent of theta 1 equals d, which is the real that would been the distance, and here the distance that we see. Now we will face the last problem. Okay, the last problem is what we know from Snell's law is with sine. So we know that n1 sine of theta 1 equals n2 sine of theta 2. So there is actually an approximation. So for really small angles, we have that sine of theta is approximately tangent of theta. Okay? And is this a case of a small angle? Yes, it is. Because he's telling you that you are looking at it parallel almost. When you look at the image of small, at the surface, he tells you over there, okay? So it is a small angle. Now of course, like, you wouldn't be deducing this formula there. You kind of needed to know it. And when you need to be used to finding this formula fast, like sine of theta and tangent of theta are really similar. Let me try to show you their graph, like, really fast. Over here, like, let's say sine of x. Okay, now look, tangent of x. Now of course the graphs are not the same. Tangent of x is not sine of x. Okay, but look for small angles. Can you see how they get really close for small angles? Like, by now you can't even see the difference by now. Now we already can see small difference. Now after and this is over here, it's x is being in radius. Okay, yes, in radius. So just so that you can see that sine of x and tangent of x are really similar for small angles. Okay, so what I'm going to say over here is that let's use this one, sine of theta 2 divided by sine of theta 1 is equal to n1 divided by n2. Okay, now as this approximately is the tangent of this and this is approximately the tangent of this, so we can say that this is equal to d divided by d. So what I'm saying right here, sine of theta 2 divided by sine of theta 1 is equal to tangent of theta 2. Now it's approximately, okay? Tangent of theta 1. Okay? Notice this n over here is from where it's going out, like from the water, and this n2 is from where it's going to. Okay? So let's just put it in here. So the distance we are seeing divided by the big distance that it would have been is equal to n2, which is this destiny, okay, divided by n1, which is origin, okay. So the distance you see divided by this distance is equal to n to the distance, the refraction index for the destiny divided by n1 refraction, the refraction distance from index of the origin, okay. So this formula over here is really helpful, so let's put it in color. You need to remember it, you would win a lot of time. Origin, no, destiny, actually destiny one, which is origin, okay. And let's put it in blue for water. Now we are going to use this formula for our question, and we solve it. Now what is our question? Well, what is small d? Small d is the distance that you end up seeing. It's 14. You look to yourself like a fish and you see it 14, okay. So 14 divided by, what is big D? Big D is the real distance that would have been, which is 20. If there was no water, where it's actually is, where the picture actually is 20, okay. So 14 divided by 20, and here it's equal to what? N2, this is the index of refraction for the destination, the destiny. Now the destiny is, it's going to the air, so the air has an index of refraction of 1, okay, over here. So it's 1, and here n1, which is the origin, which is the thing he wants from us. So n1 equals, now 20 divided by 2 is 10, divided by 7. So let's see the numbers over here. Which one will it be? 1.4 seems a good one, right? 1.4. So yes, look, I'm not good when doing fast math, so I'll do it like this. So 1, 7, 3, put this, you can gain a 0, 4, 28, 2, but you don't need to end it because 1.4 would be over here, 1.43, something like this, okay. So what's to take from this? Well, there is very good informations about the how the velocity is with regarding this Snell's law, very important. We have the law for this one over here, the small d and this and destination and origin, okay. So these two formulas and how they are, and this is a very nice, like, because you get used from solving from their book with the fish problem, things like this, but here you have a mirror, right? So you needed to find that 20 by yourself. You needed to know that the actual picture, the actual fish, let's say it's 20 centimeters depth, okay. That's it.